Because we hadn't really talked about the Nobel Prize this year.
John Martinis for the discovery of
So it was a complete surprise.
You proved that the experiment actually the first qubit in the world, is it?
Yes, that's right. And I would say it's the first qubit where we saw not just tunneling, but we saw the energy levels. And I still remember when I saw that, it's like, oh, when I analyzed the data, this is going to look really good. So that was the biggest eureka moment that I had there.
欢迎收看《投资聊一下》，我是吴彩妮。今天很特别的，我们来出外景了，看看这么绿意盎然的庭院，还有这么美丽的阳光。我现在人呢，在美国加州的洛杉矶。那为什么会来这边呢？因为今天我们要访问的是2025年获得诺贝尔物理学奖的物理学家 Dr. Martinis。在节目当中，今天我们要谈谈他获得诺贝尔奖的心路历程，而且呢，我要问他为什么想要成为一名物理学家，而且他现在是有一家新创公司 Colab， 他想要达到什么样的量子成就 ？Hello, Dr. Martinis.
Hello.
As our audience knows, we've been tracking quantum computing's progress very closely. But I think today is truly special. Why? Because we are sitting here with you, Dr. Martinis. It's a truly honor to have you on the show. Thank you for joining us.
Yeah, and thank you for coming here. I will enjoy our interview a lot. Thank you.
Thank you. This month must be really hectic for you, especially you just went to Stockholm for the Nobel Prize award ceremony, right? And then you went to Tel Aviv for your company's collaboration. So would you please share with us, how does your daily life look like after winning the Nobel Prize?
Well, immediately afterwards, it's just completely insane with many emails and requests for interviews. And that was very nice. It's a great honor for a Nobel Prize. I very much enjoyed the interviews. It's kind of funny, in the first initial days, they're usually short interviews, how did it feel, which is okay, but I really liked soon afterwards, there were 30 minutes or 60-minute interviews. Kind of like what we're doing today, where you can really get into the issues and talk about all the things that are happening. And that's been quite nice. My favorite interview in the first couple days was with a student group in Nepal from Kathmandu.
Oh, really?
Which sounded very exotic to me. And it turns out it was a high school astronomy club that interviewed me. But they asked really good questions. I was really happy to talk to the students. That was kind of really fun. Because that's normally an interview I would have never thought of doing.
What kind of questions they were asking?
I think it's going to be a lot like our interview and the other interviews. I mean, not in depth, but what was it like for the Nobel Prize, and how do you encourage students to become scientists, things like that, that were very appropriate for high school students.
So let's get back to a little bit to the moment when the Nobel Prize announced. What were you doing and when you received the news, right? So you got a call, and then what is your first reaction for it? Was it completely surprised, or you kind of expected?
When they announce it, it's 2 o'clock in the morning. So I was fast asleep. Okay, so, and I think Michel Devereux was asleep too. So it's not like we got the call right away. In my case, my wife was up reading that evening, and she kept hearing the phone ring, but she thought, oh, I'll just get it tomorrow, whatever. Because we hadn't really talked about the Nobel Prize this year, and when it was coming up and when it might happen. So it was a complete surprise. But before she went to bed, she checked her email, and there was all these congratulations. So they then knew what was going on. She let me sleep until about 5:30 in the morning. Came in and gently woke me up. She said, oh, there's going to be some reporters here in a half hour. And it's like, well, what's going on? And then I kind of put it together. But I took my laptop and opened it up and searched. And, there I was with Michel Devereux and John Clark, which was great. So, yeah, that was a surprise, a wonderful moment. I knew I had to get ready for the day. Okay, so I took a shower and got up, and then the reporters came at about 6 o'clock in the morning. and then started talking to them.
So I guess your wife didn't sleep the whole night.
No, she didn't sleep, but she didn't have to be on for the whole night. For the whole day, I had to be on. I was really appreciative that she let me sleep a little bit. But that's my wife. She tries to take care of me well.
Oh. So the experiment that won you the Nobel Prize, it's 40 years ago, right? So at that time, I would like to know, why did you choose this topic? There's a variety of topics for young graduate student, right? Why the tunneling experiment back then?
Yeah, so what happened is I had John Clark as an undergrad teaching solid state physics. And he's a great teacher. I enjoyed it a lot and we got along well. And then he told me a little bit about the experiments he was doing, which was looking at quantum noise in these electronic circuits. Electronics was kind of my hobby. I enjoyed that a lot. Besides being the hobby, as a student, you're really interested in quantum mechanics because it's a very unusual phenomenon. And you learn about it, and you're only really scratching the surface, even in a graduate course, of all the different things you can see with quantum mechanics. So I wanted to learn more about it. I wanted to do experiments in it. So I joined his group because of that. I did a starter experiment, and then about 2 years later, I went to a conference. It was LT16, low temperature 16 in UCLA. People were talking about doing this experiment. There were some previous experiments that people had done, but the results were a little bit murky and it wasn't clear and really not understood well. But of course, the whole question of whether these macroscopic systems could obey quantum mechanics, and there was maybe a chance that it wouldn't, as expressed by Anthony Leggett, that really got my attention. So I, talked to John Clark afterwards, and eventually he brought together Michelle and myself with John to do the experiment. But from the very beginning, it was a really interesting experiment, and I didn't understand why 10 or 12 other groups weren't working on this. Because for me, it was the most interesting experiment, in our field at the time.
So when you published the results, was it a big breakthrough when your team proved that quantum mechanics really exists on a macroscopic scale?
Yeah.
Did the result resonate with many other scientists, or people are still don't understand what happened for this part?
So I would say this was a well-known proposal by Leggett and others. And then when we showed it, and especially we showed it in a very complete way, that was an important experiment. I got invited talks. John and Michelle got invited talks. That was a big piece of physics. I remember there was even a small write-up in Scientific American on this. So, it was a nice experiment. But it was not at the level of let's say a discovery of high TC and other things that happened soon afterwards. But good. But what happened, it was done in a way that got other physicists interested in it, and a few people got into the field and started doing more complicated experiments, looking at other things, and then the field grew and grew over time. And it's really taken, 10, 20, 30, 40 years for the field to expand to where it's very important now. And a big part of that is the idea of building a quantum computer out of these systems.
So when you did the experiment, did you expect that would grow into a big industry or?
No, for me, we were just doing a basic experiment, showing this idea about quantum mechanics and macroscopic. We also understood that at the time you could do other quantum experiments with the system. The field would grow. It's the fact that quantum computing might be such an important technology that it has grown so rapidly. But it took, let's say, 10 or 15 years for that experiment to grow enough, to be mature enough that the field really grew fast.
But during the period of time, you still think it's so interesting focusing on this?
Well, yeah, I would say in the first 10 years, what we were doing is working out all the physics of these, what I'll call quantum devices. And there was a lot of things we had to understand, with a lot of materials issues. What's the right materials to make it out of? And things changed over time. So, and I think it was good we had 10 years to try to put down the fundamentals of the field. And that way, when the idea of quantum computing came around, and with money to funding to build it, we had a good foundation. There were lots of different things to try, which is what people in the field did. And then we could move, fairly quickly on that when the time came.
Oh, I understand. You've mentioned before that you greatly look up to Richard Feynman, right?
That's right.
Now you have won Nobel Prize just like he did. So what did he do to inspire you to feel that quantum was something probably you could work on for your lifetime?
It's actually Richard Feynman. So the story is, at the end of my graduate, when I was writing my thesis, I went to a conference in Santa Barbara, which was a nice conference on what we were doing. But the last speaker was Richard Feynman giving the talk about quantum computing. The most interesting thing is, after the talk, he was kind of mobbed by all the audience, around him, asking questions, and him talking about what he knew. And, I was just a graduate student at the time, so I was on the outside of the ring, and I could barely hear his answers. It's all the professors got close, right? What I learned from that, it was very interesting. Physicists thought it was great. If you did research in this, it would bring a lot of interest, because it was just an inherently interesting topic, especially, I would say, thinking about quantum mechanics in kind of a computer science way is what the field really did in the last 40 years. And, so I knew this was a very exciting field. To be honest, I didn't quite understand fully what he was talking about. Okay, it was still very new to me, and it wasn't put in the way that, in the really clear way, but of course Richard Feynman's a great speaker, so the whole atmosphere of the talk was wonderful and very exciting. But it took other people in the field in the next 5 years to really put a lot of the physics into it so we would understand what to do. But it still took about 10 years for there to be funding in it so that one could really start up experiments in that. And like I said, we were doing important research up until then to figure out the physics of these devices.
How did you get interested in physics? Did your parents encourage you to be a scientist?
My mom was born in the United States and a homemaker. My father was born in Croatia and came to the United States. He was a fisherman. He came from a fisherman family, which is actually very important, because if you own a boat, you're always fixing things. Okay.
Just like you did in the lab.
Yeah, just like in the lab. And you're fixing things with whatever tools you have available, which is kind of like in a physics lab. You're still developing the technology. My dad was a fireman, which is in fact, it's a dangerous occupation, but at the same time, it's very technical and mechanical, and you have to know a lot of things. So my dad surely would have been an engineer or some kind of position like that if he had the educational chances. But he loved being a fireman. It's very physical, and he ended up being a pilot of a fireboat in the Los Angeles harbor. I wanted to see if I could do well in physics at Berkeley, which of course is a top school. And I did very well and enjoyed it. That was kind of the right path for me.
Yeah, exactly.
It was interesting. My fallback plan was to go into computer science.
Oh, really?
Yeah, because I like computers. I learned how to program in high school. I liked it a lot, and I like hardware better than software. From my background, that was more of a unique skill for me. So that's where I spent my effort on.
You know how to build things together.
Yeah, that's right. Which you're doing as a scientist, experimentalist, all the time.
I understand. So you went to Berkeley for both your undergrad and the graduate school, and then you joined John Clark's team and worked together to prove that tunneling exists on a macroscopic scale. Now it's 40 years later. That breakthrough has won the Nobel Prize. So now we're diving into the core. So would you please explain to us, to our audience, what exactly is tunneling?
The easiest example of this is actually in one of the Nobel films between Michelle and I, and we're throwing a ball against a wall, and of course normally it bounces back, but according to quantum mechanics there's a small chance that it'll tunnel through the wall and come out the other side. Now normally with a regular ball it's so massive and you're not throwing it very fast, so the chance of it tunneling through is very small. But if you take electrons and very thin oxide layers in semiconductor devices, then you actually can see tunneling. And there's a lot of devices out there that use tunneling as part of their
nowadays.
And also you explain alpha decay radioactivity with it. So there's a lot of physical phenomenon that depend on tunneling and use tunneling. And then what was unusual is that instead of tunneling, for example, an electron or an alpha particle, which is a fundamental particles, you're tunneling this macroscopic current and voltages in this electric circuit that's about a centimeter across. So it was kind of a new application of quantum mechanics to a new system. There's always behavior quantum mechanics, and then you measure it and observe it. So you could see that it was tunneling out of this certain macroscopic state in a way that couldn't be explained by the normal thermal activation process, a classical process. So you saw some extra tunneling rate from this. And we did a very careful measurement to measure the parameters, design the experiment properly, do lots of checks to make sure it wasn't some other phenomenon like noise, for example. What was interesting about that is we started it out right away doing very simple experiments at higher temperatures, 1 to 4 Kelvin. We put it together in this simple-minded way, and it was a total disaster. It didn't work at all, didn't make any sense. We immediately knew that we just designed it wrong. And then what we understood is that this was a microwave experiment. You had to filter against room temperature radio and microwaves getting in. We had to shield it well. We had to design it, so that the microwaves were very well controlled. So we spent some time really thinking carefully about that. We went to the astronomy department and used some of their microwave equipment just to understand. We read books. And then we redesigned it, and I think it was a few months later, then we took the data and it looked just great. It made sense. And we knew on the right track. And then at that point, it was just building the low temperature dilution refrigerator cryostat in order to take the data. But I'm going to say after that, it was kind of step by step, verifying that was working, and we got to the experiment. So it wasn't necessarily a eureka moment, other than in the beginning when we understood that we were just thinking about it all wrong. And the thinking that led to the success, that is, I think, the greatest idea we presented to the physics community as the way to think about how to do the experiment. I do remember one moment for myself, and this is actually taking a bunch of data. I was looking at a new kind of device with a higher critical current, and I had just cooled it down, and I kind of turned on the electronics. And instead of there being a series of dots representing transition to the voltage state, you could see that there were 3 main dots there. And those 3 main dots were the 3 peaks that you see in the energy level paper. And that's probably the most compelling data we had in all the experiments, to see those 3 peaks and then to show exactly what's going on there. And I still remember when I saw that, it's like, oh, when I analyze the data, this is going to look really good. So that was the biggest eureka moment that I had there. Well, you can see the current flowing through the device, and the current flowing. What happens is you can flow current through the device, and then there'll be zero voltage across the device. So this is a supercurrent. That's what a superconductor is. But if you have the current too large, then you'll start seeing a voltage across it. It's kind of looking like a regular metal then. And then what happens is slightly before it hits what's called the critical current, where it always goes across, you can have either the temperature causing it to go to the voltage state or quantum tunneling, allowing it to go to the voltage state. And that's where the physics happens. It's the escape to the voltage state by a quantum phenomenon. And that's the simplest way to measure this quantum phenomenon. What was thought of by Professor Leggett in the 1980s and really perfected, the measurement perfected by us. And then that led to other experiments over the years.
So you proved that the experiment actually the first qubit in the world, is it?
Yes, that's right. And I would say it's the first qubit where we saw not just tunneling, but we saw the energy levels. And the energy levels means there are certain oscillation frequencies that tell you that it's obeying quantum mechanics. So in some sense, that was the first qubit. However, it wasn't until, let's say, 10, almost 15 years later, that there was a group in Japan that built it a slightly different way and was able to see even more clear observation of a qubit behavior. And it just took a while for us to understand how to build that system properly. But yes, I think we laid the foundation for all of that, which is why we were awarded the prize.
Which is great because you lay the foundation for all the quantum computing that people are doing, producing qubits.
But I have to say, many people contributed this.
I understand.
And I think what happened in our experiment is we did the experiment in a way that it was very clear what the physics, and we more or less combined quantum mechanics with microwave engineering and electrical circuits in a way that it was kind of clear what the physics was going on, so that it could be built upon by many other people. So, but we were to build a quantum computer took many people, many experiments to slowly understand how to build everything.
Yeah, we understand because I think it's apparently linked to my next question, because look at your career, you're not only working on theories, right? You did build up quantum computers from scratch.
I'm mostly an experimentalist. I have done some theory, and I would think it's partly explaining your experiments in a simple enough way that people can intuitively understand it. So we've developed a lot of theory concepts to make that understandable. You want to be able to describe what you're seeing in a simple enough way so that you can envision something more and more complicated over time. 50 qubits to 100 qubits. When would you get to 1 million qubits? I'm going to be dead, okay?